you people out there in podcast land. Good to talk to you again. And now we're starting chapter two. Now remember, chapter one is basically your just a little introduction, and don't make a big deal out of it. We just went through some terms and so forth, but now this is where we need to really get roll our sleeves up. Linear programming. Now, some of you engineers might be really bored stiff with this because you've done this before, so bear with us. I'm going to take this from the bottom up because there's some people that have never seen linear programming before. And like I say, I'm just, the second book is just, I want to expose you guys to a lot of different concepts, a lot of different analytical and quantitative tools so that if you're at a meeting or something and people are talking about this and that and this and that, you'll understand. If they talk about linear programming, queuing, networking, and so forth, you'll understand what they're talking about and be able to have a discourse. Uh, okay, let's get started. Steps in developing a linear programming LP model. Formulation, solution. Now the formulation is putting the problem in more or less a simple mathematical expression. Notice I said simple. Try to keep things simple, guys. The solution is concerned with once you formulated your problem in a mathematical model, uh, the solution is going to be the solution is a translation of that model into either maximizing, optimizing that solution, whether you're maximizing profit or minimizing cost. And the sensitivity analysis interpretation, make sure you understand the output, make sure you can look at tweaking it and ask what if questions, because you always want to be able to be thinking outside of the box, of course. That's just, the mathematics are fine, but you have to be able to control the mathematics, and sensitivity analysis gives you that opportunity. Now, remember, always use your common sense in solving problems and looking at solutions. So, properties of an LP model. Um, yeah, seek to minimize, for example, minimize cost or maximize profit or whatever you're looking for um, achieving here. You always have constraints or limitations. For example, there are only so many pieces of metal you can use. You only have so many hard drives. Only have so many people that can put machines and things together. And so you have constraints and limitations. Uh, there must be alternatives available. And yeah, there are always going to be choices that you need to make decisions and so forth. And that's what the linear programming is all about. If you make three or four different types of products in the linear programming, it's going to tell you based on all of your alternatives available, which are the best choices. Where should you put your all of your resources into which products in order to make the most money. And the fourth property is that all of the equations are linear. There are no quadratics, no square roots, no cube roots, or anything like that. It's all linear programming. It's amazing, actually, how this works. Um, Here's an example of a linear programming formulation. The decision is for example, how many products, how much to make of each product if you have two or more products. That's the decision. So that's usually called the decision variable or the decision choice. He uses the word decision variables here. The objective is, in this case, maximize profit. Now, it could be minimizing cost of making the products. How do we minimize the cost? But he's framing this objective into maximizing profit. And we'll look at some minimization linear programming problems also. The constraints are going to be the limited resources. So these are the three parts of the formulation of a, for example, let's call it a product mix problem. The decision variables, the objective function, and the constraints, however many there may be. Now here's an example. Let's look at this example here. The Flair Furniture Company, they have two products that they make, tables and chairs. The decision, how many of each to make this month. The objective, maximize profit. Okay, here's the data, Flair Furniture Company data. For each table that you sell, you get $7 profit. Okay, for each table you get $7 profit. I need to change the color on this, don't I, guys? Let's make it more like this color because the screen is that better? That's too dark. Okay, we're going to get this here in a minute. This is going to be really cool. We'll get a cool color here. Okay, so you get $7 profit for tables, $5 profit for chairs, for each chair you sell. Carpenter. The carpenters take 3 hours to make tables, 4 hours to make chairs. And can you see where that is? I still like yellow, guys. I'm sorry. I'm just so fickly here. We're going to keep it at yellow. So it's in the painting, it takes 2 hours to paint a table and 1 hour to paint a chair. Okay, but you only have 2,400 hours available for carpenter work and 100 hours available for painting. That's all the time that these guys can give you. Uh, Now, the decision variables. Now, how do we translate this information into a linear mathematical model? All linear equations. Okay. The decision variable is, remember, the three parts: decision variables, objective functions, and constraints. The decision variables for this particular product mix problem is the number of tables to make, number of chairs to make. The objective function is written as a uh, linear equation here, 7t plus 5c. How do we maximize that profit there? In other words, how many tables do we make and how many chairs do we make? These are the decision variables in order to maximize the profit here. So how many tables and how many chairs do we make in order to maximize the profit? Now, hold on 1 minute, guys. Let me get this. Okay. Now the constraints, since we only have 24 hours of carpenter time available, you write that as 3t plus 4c has to be less than or equal to 2,400 hours. It cannot exceed more than 2,400 hours. The same with the painting time available. You only have 1,000 hours. So since it takes 2 hours to paint a table and 1 hour to paint a chair, the combination of painting tables and chairs must be less than or equal to 1,000 hours. Same as the combination of building tables and chairs must be less than 2,400 hours. Notice they're all linear equations. Now, there are more constraints here. And the non-negativity constraint, let's talk about that first. This simply says that you have that t and c, you cannot build a negative number. This just makes the case that you can't make a negative. Remember, matter cannot be destroyed. So you cannot um, uh, make negative numbers of tables and chairs. Now, the other constraint was that you want to make sure that you make no more than 450 chairs and you make at least 100 tables. So notice the inequalities here. Say this is how you say those things mathematically. So if you make no more than 450 chairs, that means C must be less than or equal to 450 and so forth. Okay, here's the complete summary of all of the linear equations that we're using here. The decision variable is how many tables and chairs to make. The objective function is to maximize 7t plus 5c for profit, maximizing profit, subject to these constraints: the carpenter constraints, the painting constraints, the maximum number of chairs, the minimum number of tables, and then the non-negativity constraints. I think I will change the color, guys. Let's see. Y'all like that better? I like that. I like that. Excuse me, please. Okay, I like that color better. I've got it really tough just trying to decide what color I want to highlight in, right, guys? Okay. No. So first thing we want to look at now, this is a simple two-dimensional problem because we only have two decision variables. So I just want to give you a feel for what's going on here by showing you the graphical solution first, graphing this LP model. And so like he says here, while this can only be done in two dimensions, the same basic concepts apply for any linear programming problem, integer programming, linear programming, networking, all the little situations we're going to look at where we're using um, LP mathematical models. It's all basically it's just more of it, more dimensions, but you can't graph. Well, you can graph it, but it's very difficult. He claims that you can't. Well, he says, well, this can only be done in two dimensions. I've actually seen some that done in three dimensions, but that's besides the point. We're not going to worry about that because we're going to let Solver work these. I want to show, make sure you've loaded, I know you by this point you've loaded data analysis with your Excel add-ins. You also need to go and load your solver for the Excel add-ins and make sure that's loaded in because we're going to be using solver. Okay, the carpentry constraint line. Now the best way to draw, just to help, I know some of you know this like the back of your hand, but some people, believe it or not, have forgotten this stuff. What you want to do basically is to solve this linear equation here, this one here, you want to take t, for example, and set t equal to 0. If t is 0, then you divide both sides of the equation, if you remember, by 4, okay, to solve for c. So if t is 0, c is equal to 1/600. So that's what this is right here. And likewise, if you set c equal to 0, then t is 800 if you solve the equation for t, and you get this point here. Once you have this point, you draw the line, which you see right here, and the feasible region, since this is the carpenter, well, let me point out one thing. Notice when he solves this equation, he's using the equal symbol, but the actual constraint said less than or equal to. Since it's a less than or equal to constraint, the feasible region is in green, is in the green area here, since it's less than 2,400 hours, okay? Since it's less than. So that's our feasible region. If we only had one constraint, you could build any number of tables and chairs at any point, guys, within the feasible region, okay? So you could pick like, let's pick a safe point here, like you could go out to 500, make 500 tables, and for example, probably safe to say 200 chairs. So yeah, but is that the maximum number you can make? No, the maximum number is going to be somewhere along this line here, guys. Somewhere along that red line is going to be the maximum number we can make. But now we've got to add the rest of the constraints and see what the intersection is. Let's add now the painting constraint. Now remember, we already have the carpenter constraint, and we solved the painting constraint the same way we solved the carpenter constraint. First by setting t0, then solving for c, we get this point right here. And then setting c equal to 0 and solving for t, we get this point here. So now look at the intersection. Now our feasible region is diminished to this area here. And I'll tell you, here's our maximum point. But I mean, that just comes from experience, but that's going to be our maximum point. If you find the intersection of these two lines, then that's the maximum point. But remember, we have to add the next constraint. So we've got the carpenter constraint and the painting constraint added on to this point. And notice here's the linear equation. Now, notice, remember now, that's not a linear equation. It's really an inequality, and that's why it's everything to the left of this. Okay, it's everything to the left because the actual constraint was a less than constraint. In other words, 2t plus 1c is less than or equal to 1,000. But you just set it to an equality in order to solve, to find the 2 points in order to draw that line from here to here. Okay, now we're down to adding the maximum number of chairs, which is a parallel line to the t-axis or the x-axis, as the case may be. Hold on 1 minute. I think I'm going back to yellow, guys. No, I'll try orange. I don't know. I don't like orange either. Okay, this is pitiful. I'm going to stick to orange for a while until someone complains. Okay, now, notice that when we add this line across here, if C is equal to 450, this is the line that says C is equal to 450. So it doesn't matter. In other words, what T is, C is always 450, which is this parallel line here to the x-axis. So notice now how our constraint now is this feasible region, all below it, since C must be less than 450, less than or equal to 450. The feasible region is below here, below this line. Now, the minimum table line says that you have to have at least 100 tables. So now that's a parallel line to the y-axis, which is this line right here. And notice that now, since that's a greater than symbol, it's everything to the right of this line. So greater than 100, that means that T must be greater than 100. You have to have T has to be greater than or equal to 100 tables. So that's everything. So this becomes our feasible region, guys, in the green area here. See, and the non-negativity constraint simply means that this is in the first quadrant. Everything is in the first quad. Remember, the first quad is where x and y are both positive, okay? Where you have x positive, y positive. So that's the non-negativity constraints, is assuring that everything's in the first quadrant, and not this one. This is the negative plus quadrant. This quadrant here is the negative, oopsie, the negative, and this is the plus negative. So we're in the plus quadrant. Okay, let's keep going here and see what happens. Now, this was where we want to stop at this point, because I want to start here and show you how to find the optimal point. This really doesn't do it justice. I want to show you an example. I want to write out some things here. So we're going to continue at this slide in the next podcast. Take care, my friends. Let's see here, right?